So at Fraunhofer Institute for Laser Technology, we thought up a new idea how lasers can help your printed electronics process to achieve better quality control and error correction in line. And we patented this, and this is like a first peek into this. So yeah, why use lasers? So the typical advantages are the high heating or cooling rate, the very short interaction time, and the ability to work on heat-sensitive substrates. And as you can see here, this little peak here is the laser process, and this is an oven process. And the area under the curve is, of course, corresponds to the energy. The oven usually heats up the whole room or the whole building. So you save all that energy with the laser. And also compared to photonic curing, you have similar advantages. You have also the ability to be more selective, to match the ink formula to the wavelength you're using, and again, to be selective about resintering. And this is the point of this talk. So we're going to do pre-sintering and resintering. And these are the sensors we worked on. Just as an example, we did those strain gauge sensors, which have, of course, many advantages compared to the conventional sensors, which have to be manually glued on every time. Some suppliers ship parts from Europe to the US just to have them glued on by experts and back. So yeah, there's real demand for this, but there's still some problems because the printed sensors don't meet the strict quality requirements that users want and that they are used to from those sensors that are produced in vacuum processes. So we want to address that. And before we had this new terahertz measurement technique that I'm going to show you soon, all we could do is basically this. So we have some printing process and we have pre-sintering with low energy to achieve some low conductivity, so we can measure something. Then we measure it with a 4-point probe or multimeter, and then we do post-sintering based on that. So with this, we can only adjust quality from one part to another, so they are more consistent, but not within a part. And those are inkjet printed samples, but it would work with other processes too. Silver nanoparticles with relatively thin thickness and 150 micrometer track width. And the goal later is to do something like this. This is just a rough sketch, but I'll show it to you in practice soon. To have, like, within a part, you have some areas of different conductivity. Then you measure that, you create a map of this, and then you do resintering, and for each pixel you match the laser parameters so that in the end it's more homogeneous. Yeah. But before we get to that, let's just look at what a typical laser process looks like, what the parameters are. So you have the laser pattern, the tracking speed, the scanning speed, the laser power, the spot diameter. We use a process where the scanning speed is pretty fast, so the part basically sees something similar to a line. And we use the continuous wave laser, so not pulsed, with a near infrared wavelength and a minimum focus of 52 micrometer, but we worked out of focus. Yeah, and you probably have seen something like this before, a typical graph, how the resistance depends on the power during sintering. It comes down here from infinity, and then there are different parts, different regions, where you have first sintering, then partial melting, and then you damage your part because the power is too high. And we want to stay within this region, where we just have sintering. So usually those processes aim at optimum conductivity. We don't do that, we stop short of that, because we want to still have room to control our conductivity. It's not quite easy because this looks almost exponential, so we have to really know this, and that's why we did these tests. This looks like the same graph again, but as you can see here, it doesn't go up to infinity. It intersects with the